Okay, welcome to the video number 4 on traffic assignment, which is your module 6 traffic assignment. So here we are going to talk about a method called stochastic assignment. It's a method of traffic assignment, stochastic. So what are the theoretical basis for this is if you have two routes between a zone A and B, not everything will go only on one link. So some people are going to use, so it's going to be probabilistic, which is hence the term stochastic comes. I think they are interchangeably used. Probabilistic, stochastic, they're interchangeably used. So that's essentially what it is. If you have travel time associated with each path, of course, every path will. So that travel time could determine the utility of that path. So if you have, the utility theory, we talked about logit models in mode choice. If you extend the same logic, travel time as a utility or disutility, depending on which way you want to put it, and logit model formulation could give you a solution for traffic assignment problem, and that's what we are studying. The formulation is very simple. You already seen it. It's very simple. If you can associate a utility with each path, say this is for path 1, and you can associate utility for path 2, and then if there is a third path, you will have U3. So the probability of going by path 1 will be exponent of E path 1, a utility of path 1, plus sigma of all the exponents of all the competing paths. You've seen this before. That's exactly what you will. Here's a simple example. A to B, 3 routes, 7 minutes, 8 minutes, 9 minutes travel times. Route 1, route 2, route 3. And the simplistic assumption will be U1, utility of route 1 is negative of its travel time. Why we are putting a negative value? That's because it's a measure of disutility. The higher the value, it's more penalized. So if you put a negative value, it is indicative of disutility. So we use this to do the stochastic assignment along these paths. Oh, by the way, in earlier slide, it says there are 100 trips between A and B. So that's what you need to assign. So you're all too familiar with this. Travel time as a utility of path 1 is -7. In the previous slide, we have indicated it. Utility of path 2 is -8. So you go through this, you have the probabilities of 66.5%. So if you multiply that with number of trips between A and B, you get 66.5, might as well call it 67. The same multiply with 100, you get 25, and here this guy gets 9 trips. So your traffic assignment on this network is this guy got 67 trips, route 2 got 25 trips, and route 3 got 9 trips. Simple enough, right? Let's see the complications. What are the complications? Oh, sorry. Before we get to the complications, here is a challenging question. I introduce you to a regular trip a fella I know makes. Route 1 for him is 14 minutes. The other route takes 15 minutes. So sorry, no need to write there. So 15 minutes, and the third route takes here. Third route takes 16 minutes. So given this, and we just worked out this problem, correct? You got this route has 67%, this route has 25%, and this route has 9%. So can you quickly tell me what is going to be the choice probabilities of this fellow on these three routes? What is the probability of his choosing this route? Very simple. If you look at these travel times, they're 14, 15, 16 minutes, 7, 8, 9 minutes. That's why I deliberately chose this. Adding a constant to utility functions is not going to change change the property of the choice probabilities at all. So essentially, if you subtract 7 from this, each one of the travel times, your problem is that essentially reduces to what you just solved, and your probabilities on this particular real world scenario are going to be 67, 25, and 9. It's that simple. So now, advantages and disadvantages. It's very realistic. This is how things work in real life. But competing path identification, if you look at those three paths I said, those are only three paths just Google gave me. But I know there are at least 7 different ways I could get here. And I do get, oh, I gave away who that is. Well, never mind. 7 different ways you can use that. I can come there. So which one of them are really my competing alternatives? It may be for the traveler, they know what those competing alternatives are, but to develop a algorithm that picks up, that goes into the traveler's mind and finds them, it's impossible. And once you identify those paths, you have to find a utility function and then do a lot of multinomial formulation, etc., etc. Computational complexity is going to be horrendous. So this is not often done. Well, some of the new techniques are using this, but it's not very often done. Eventually, probably a couple of decades from now, everybody uses it. I don't know. All right, so that is where our video number 3 ends. Oh, all right, this is where our video number 4 ends. I'll see you in video number 5.